Good morning. Today we are going to explain you Milankovitch cycles. My group is conformed by Julian Joya, Natalia Blanco, Wilmer Garcia, Elías Machado, Camilo Ardila, Cristian Correa, Giovanni Abril, Luis Gaitán, and me, Alejandra Ortiz. In addition to the rotational and translational movements, the Earth exhibits other minor, though imperceptible movements with consequences on the climatic change undergone during the geological past. Milankovitch in 1941 published a connection between the movements of precession, obliquity, and eccentricity with the great climatic changes and glaciations. Each of the orbital movements presents a periodicity, detectable by means of geological or geochemical data. However, later processes in the sediment, diagenesis, overlapping cycling patterns, or the so-called lithological noise, affect the accurate detection of Milankovitch cycles. Once the orbital patterns are established in the sedimentary record of a basin, this cyclostratigraphic tool is very suitable in lithological and temporal correlations, demonstrating the usefulness in the analysis of source and reservoir rocks if oil within the petroleum system.
Cyclostratigraphic. The cyclostratigraphic is the study of period process recorded in stratigraphic successions, and this discipline has experienced a rapid development concerning the recognition, characterization, and interpretation of astronomical force climate cycles. However, the cyclostratigraphic tries to identify cycles that more logical have a defined periods and whose reflection in the sedimentary series can be determined by cyclical change in the phases that exist in one or more of the elements that define them, how for example lithology, geometric structure, paleontological context, and other things that can related with the stratigraphic. Next, cyclic change in chemical or physical properties that can vary independently of whether the phases do, such as the isotopic composition of the carbonates or the magnetic characteristics of the sediments. In this picture, we can see the study of the cyclostratigraphic through the study of the orbits that help us to identify the behavior of the cycles, taking into account variables such as time and period. The three main goals of cyclostratigraphic are: first, to construct an astronomical timescale which allows to calibrate the geological timescale with an unprecedented resolution. Second, to improve the knowledge about climate change operated at those timescales, their causes and consequences, and in particular about the behavior of the climate system in the light of the resultant change in seasonal insolation patterns caused by orbital parameters. Number 3, to increase understanding on the positional mechanics of sediments and the dynamics of sedimentary systems. Climatic cycles. The climatic cycles are related to climate change that affect large regions and are expressed in repetitive sedimentary change. So in this picture we can say variables like insolation, temperature, and venting that can help me to identify the different changes in the sedimentary.
The Serbian astrophysicist Milankovitch is best known for developing one of the most significant theories relating air motions and long-term climate change. Born in 1879 in the rural village of Der, then part of the Austro-Hungarian Empire, today located in Croatia. Milankovitch attended the Vienna Institute of Technology and graduated in 1904 with a doctorate in technical science. After a brief stint as the chief engineer for a construction company, he accepted a faculty position in applied mathematics at the University of Belgrade in 1909, a position he held for the remainder of his life. Milankovitch dedicated his career to developing a mathematical theory of climate based on the seasonal and latitudinal variation of solar radiation received by the Earth, now known as the Milankovitch theory. It states that as the Earth travels drawn space around the Sun, cyclical variation in three elements of Earth's Sun geometry combine to produce variance in the amount of solar energy that reaches Earth. Variation in the Earth's orbital eccentricity, the shape of the orbit around the Sun, change in obliquity, changes in the angle that Earth's axis makes with the plane of Earth's orbit. Precession, the change in duration of the Earth's axis of rotation. The axis of rotation behaves like of the spin axis of a top that is winding down. Hence, it traces a circle on the celestial sphere over a period of time. Together, of the periods of their orbital motions have come known as Milankovitch cycles.
Milankovitch cycles. The episodic nature of the Earth's glacial and interglacial periods within the present ice age have been caused primarily by cyclical changes in the Earth's circumnavigation of the Sun. Variation in the Earth's eccentricity, axial tilt, and precession comprise the three dominant cycles, collectively known as the Milankovitch cycles, for Milutin Milankovitch. It is of primary importance to explain that climate change and subsequent periods of glaciation resulting from the following three variables is not due to the total amount of solar energy reaching Earth. The three Milankovitch cycles impact to the seasonality and location of solar energy around the Earth, thus impacting contrast between the seasons. Axial tilt. The axial tilt
is the second of the three Milankovitch cycles. About the axial tilt is the inclination of the Earth's axis in relation to its plane of orbit around the Sun. Oscillation in the degree of Earth's axial tilt occur on a periodicity of 41,000 years for 21.5 to 24.5 degrees. As shown in the following picture, on the left, can you see the 24.5 degrees, and on the right, 21.5 degrees. Today, the Earth's axial tilt is about 23.5 degrees, which largely accounts for our seasons. Because of the periodic variations of this angle, the severity of the Earth's seasons changes. With less axial tilt, the sun's solar radiation is more evenly distributed between winter and summer. However, less tilt also increases the difference in radiation receipts between the equatorial and polar regions. As shown in the picture, 10,500 years ago, the degree of Earth's axial was 24.5 degrees. Actual, the degree of Earth's axial is 23.5 degrees, and in 10,500 years will be 22.1 degrees. One hypothesis for Earth's reaction to a smaller degree of axial tilt is that it would promote the growth of ice sheets. This response would be due to a warmer winter, in which warmer air would be able to hold more moisture and subsequently produce a greater amount of snowfall. In addition, summer temperatures would be cooler, resulting in less melting of the winter's accumulation. At present, axial tilt is in the middle of its range.
Milankovitch cycles can be identified in the stratigraphic record in three ways. The first way is counting the cycles. It's the simplest method. The cycles can be counted in an outcrop, it's a nucleus, or in a geophysical record. The second way is the time analysis, through the use of Fourier analysis, which allows the identification of the dominant frequency through the curve constructed from others. And the last way is the relationship of cycles, the quotient between the cycles of precession, obliquity, and eccentricity is 1,248. Therefore, this relationship is sought in their sedimentary sequences. Eccentricity. The first of the three Milankovitch cycles is the Earth's eccentricity. Eccentricity is simple, the shape of the Earth's orbit around the Sun. This constantly fluctuating orbital shape ranges between more and less elliptical, 0 to 5% ellipticity, on a cycle of about 100,000 years. This oscillation from more elliptic to less elliptic are of prime importance to glaciation in that it alters the distance from the Earth to the Sun, thus changing the distance the Sun's short-wave radiation must travel to reach Earth, subsequently reducing or increasing the amount of radiation received at the Earth's surface in different seasons. Today, a difference of only about 3% occurs between aphelion, its farthest point, and perihelion, its closest point. This 3% difference in distance means that Earth experiences a 6% increase in received solar energy in January than in July. The 6% range of variability is not always the case. However, when the Earth's orbit is most elliptical, the amount of solar energy received at the perihelion would be in the range of 20 to 30% more than at aphelion. Most certainly, these continually altering amounts of received solar energy around the globe result in prominent change in the Earth's climate and glacial regimes. At the present orbital eccentricity is nearly at the minimum of its cycle. The eccentricity of the Earth's orbit follows a long 100,000-year cycle. The eccentricity varies from a minimum of 0.005 to a maximum of 0.0607. The larger the eccentricity, the greater the difference in solar radiation that reaches the Earth at perihelion versus aphelion. At its current value of eccentricity 0.017, this difference is 6.7%. It's thought that over the long term, the change in eccentricity can affect the Earth's climate.
Precession. The third and final on the Milankovitch cycles in early precession. Precession in the Earth's slow wobble as it spins on axis. This wobbling of the Earth on its axis can be likened to a top running down. At beginning, the wobble black and form on its axis. The precision of Earth wobble from pointing and Polaris North Star to pointing and the star Vega. When this shift to the axis pointing and Vega occurs, then wall them by considering the North Star. This top-like wobble on precession has a periodicity of 23,000 years. In the image you can see that the periodicity occurs with a time of 23,000 years, which the Earth is rotated along the line of the equator at an angle of 23 degrees with respect to the axis on the Earth. It's also shows how 10,500 years ago in the early and greater summer and less winter, and that nowadays the Earth is more winter and less summer. Due to much wobble, a climatically significant alteration must take place. When the axis is tilted toward begin the position of the north hemisphere. Winter and summer solstices will coincide with the aphelion and periodion, respectively. This means that the north hemisphere will experience winter when the Earth is further from the Sun and summer when the Earth is close to the Sun. This coincidence will result in great season contrast. At respect, the Earth is periodically very close to the winter solstice. Three are two chem precession effects. Axial precession sends an animal hair, in which the torque of the outer planets extends of the Earth. Equatorial bolts force the rotation axis to wobble, like a speaking stop. There is also an Erling presents, in which the ellipse of the Erling itself rotates about of Fox. This means that the elliptical shape of Erling orbital rotates with the long and short x of the ellipse rotate showing in space. This moves the position of appellate and parallel. It is to note that under precessional cycle, the second in solar radial stringing the air in opposite is each hemisphere, unlike the case of obliquity where an irregular teeth will mean more intense radial at both poles and the planet revolves around the sun, although obviously at local summer both poles and tugs on different points the orbit. Furthermore, eccentricity modulates the effect of process of zero electricity. The precession angle is irrelevant.
Para realizar un análisis de los datos obtenidos por los ciclos de Milankovitch, es necesario realizar un análisis espectral. Un análisis espectral consiste en descomponer una señal en sus diversas componentes en un dominio frecuencial. Este análisis nos permite determinar patrones patrones cíclicos o las interferencias que sufre dicha señal. Estos patrones o interferencias son de un tamaño mesoscópico, lo cual hace que su determinación por medio visual sea casi imposible. Para poder obtener estos parámetros se van a utilizar diversas herramientas matemáticas.
Estas herramientas matemáticas permiten pasar de un dominio de tiempos a un dominio frecuencial. Sabiendo esto y sabiendo que una función periódica se puede escribir de la siguiente manera, donde n va a ser los valores hasta infinito. Una de las herramientas matemáticas que se va a usar para este análisis es el análisis de Fourier, trabajando con el concepto de que cualquier función periódica se puede representar como la combinación de cosenos y senos de una onda. Al desarrollar la ecuación de Fourier para estos casos, se tiene que la ecuación quedaría de la siguiente manera. Así quedaría descrita, desarrollada la ecuación de Fourier para los casos de los patrones cíclicos, en donde los coeficientes AN y B sub n van a representar lo que sería la amplitud de la onda de dicha señal que se va a estudiar.
El principal problema del análisis de Fourier es que toma la tasa de segmentación como si fuera constante. Pero en la vida real, la tasa de segmentación varía dependiendo del tipo de grano. La tasa de sedimentación de grano fino comparada con la tasa de sedimentación de grava o arena, se puede observar que es relativamente inferior con las mencionadas anteriormente. Esto ocasiona unos cambios en la frecuencia de la señal repetitiva, lo cual genera ruido litológico.
Uno de los problemas más difíciles en la detección e interpretación de los patrones cíclicos es el ruido litológico. ¿Y en qué consiste este ruido? Este ruido consiste en los eventos aleatorios que dejan una huella sedimentaria y en los cambios no usuales que alteran los procesos sedimentarios evidentes. El origen de este problema, en la mayoría de sus casos, viene determinado por la observación que hace el geólogo en la zona que se va a estudiar. Por lo tanto, vamos a ver cómo sería su efecto en las ecuaciones o en los cálculos que se deben hacer. Para una ecuación que describe un patrón cíclico de una forma genérica como la siguiente, donde esta ecuación se asemeja a lo que sería un movimiento armónico simple o la elongación de un punto dentro de una frecuencia, sería que tocaría a esta ecuación adicionarle lo que sería el error provocado por esa mala observación o por la complejidad del proceso sedimentario. Para hacerle la corrección a esta ecuación, tocaría arreglarla y cambiar una variable, que sería la variable del error, que quedaría, ya no quedaría dependiendo del tiempo, sino de la variable a corregir. Ya, x de z en donde este término va como a corregir, como ya había dicho, los errores que se pueden hacer en todo el proceso del reconocimiento de la zona. Cabe resaltar que sin importar el parámetro que se tome como indicador de ciclicidad, ya sea como la temperatura, concentración de elementos, cambios geoquímicos, marcadores fósil o cambios litológicos, jamás se va a alcanzar un 100% de fidelidad en las variaciones que se presenten en ambientes cíclicos.
Otro factor que también afecta a los patrones cíclicos es la diagénesis. Debido a que los procesos diagenéticos que sufre el sedimento van a variar los patrones cíclicos que éste tenía desde su origen, debido a los cambios físicos o químicos que éste puede llegar a soportar. Esto va a originar unos cambios en su geometría, ya sea lámina o en los extractos.
Un claro ejemplo de los efectos diagenéticos se pueden encontrar en las secuencias carbonáticas en su proceso de diagénesis. Esto ocurre cuando hay lugar a los procesos de disolución, en donde hay un flujo de iones disueltos que migran a estratos suprayacentes y logran una precipitación. Esto tiene efectos en donde se van a crear nuevos patrones alternados y van a afectar los patrones cíclicos generales.
Application of Milankovitch cycles to the oil industry. Through the Milankovitch cycles, we have a field of study in which the sedimentary deposits that act as basin filling Kellet sequence are interpreted in a framework of Eustachians, sedimentation and subsidence, over time to correlate the strata and predict stratigraphy of relative unknown areas. The sequence tends to show the cyclicity of variation in the relative level of the sea and generalized unconformities, sedimentation process and sediment surge, climate and tectonic activity over time. In addition, the identification of these cycles allows geologists to develop high-resolution geochronological and chronostratigraphic timescales. Eustacia. Set of movements, negative or positive, of the level of the sea due to a variation of the volume of the ocean depression or of the global volume of the water. Transgression. Horizontal movement inland of the coastline, or advance of the sea over continental areas. Regression. Horizontal movement offshore of the coastline, or advance of the emergent areas of the sea. Retrogradation. Decrease of the gradual growth of the sedimentary bodies towards the outside of the basin, towards the coast. Progradation. The base for gradual growth of the sedimentary bodies towards the interior of the basin, towards the sea. A gradation, vertical superposition of the sedimentary layers. In reservoir rocks and in well drilling, Milankovitch type cycle patterns have been used. Thus, the higher resolution obtained from calibrate age-stroke orbital cyclicity analysis allows a great precision of the age-depth relationship. In this way, better correlation with two well can also be carried out, and a more detailed understanding of the evolution of the basin and therefore of the oil system. Other hydrocarbon parent rocks such as the Luna Formation of the Maracaibo Lake Basin or the Kimberley Clay Formation in the North Sea have been studied in the Tail-Rock, the Milankovitch and Sub-Milankovitch shackles. Kimberley Clay Formation in the North Sea. An example of the application of the Milankovitch cyclicity in a reservoir is given by the Mississippian limestone, characterized via eternally stratigraph of high-frequency sequence tins of metered zinc, together with cycles of a few, caused by fluctuation in the eustatic level. Within the Milankovitch cyclicity, the patterns of sedimentary staking correspond to the cycle of the 4 and the 5 order.
We've learned in previous videos that relative to the orbital plane around the sun, or the plane of Earth's orbit around the sun, the Earth has a certain tilt. So let me draw the Earth's tilt relative to that orbital plane right over here. So if this is the orbital plane right over here, so we're looking right directly sideways on this orbital plane, right sideways along this orbital plane that I've drawn in orange, and maybe at the point in Earth's orbit right now, maybe the sun is to the left, and so the rays from the sun are coming in this general direction. We've learned that Earth has a certain tilt. Earth has a tilt, and when I mean that, it means if you think about the axis around which it's rotating, it's not straight up from the orbital plane. It is at an angle. And let me draw that. So if I were to draw an arrow that's coming out of the North Pole, it would look like that. And maybe I'll draw an arrow coming out of the South Pole. And the Earth is rotating in that direction right over here. And you notice this axis that I've drawn this arrow on, it is not straight up and down. And right now it is an angle it is at an angle of 23.4 degrees with the vertical, with being straight up and down. And we've learned how this is what is the primary cause of our seasons, in that when the northern hemisphere is pointed towards the sun, it's getting a disproportionate amount of the solar radiation. Whatever is going through the atmosphere has to go through less atmosphere, and the things in the northern hemisphere are getting more daylight. And when you go into when the Earth is on the other side of the sun and the northern hemisphere is pointed away from the sun, then the opposite is going to happen, and the reverse is true for the southern hemisphere. But in that video, when we talk about how tilt can affect the seasons, I also kind of hinted a little bit that this is the current tilt right now, and over long periods of time that this tilt will change. And in particular, it will vary, and even the boundaries for this varying are different for the past million years than they will be for the next million years. But it varies roughly between 22.1 degrees and 24.5 degrees. And just to make it clear that it's not wobbling back and forth like this, and just to visualize 22.1 versus 24.5, it's not a huge difference. So if this is 23.4, and I'm not measuring exactly, maybe pointing in this direction, maybe pointing in that, maybe 22.1 would look something like that. In fact, I've exaggerated it. And maybe 24.5 would look something like that. And so it's not a huge difference, but it is enough of a difference, so we believe, to actually have a significant impact on what the climate is like, or what the seasons are like, especially in terms of how how much of a chance different parts of our planet have a chance to freeze over or not freeze over and all the rest, or how much sunlight they get and all the rest. So it has some impact, but I want to make it clear that it takes a long period of time, that it actually takes 41,000 years to go from a minimum tilt to a maximum tilt and then back to a minimum tilt. 41,000 years. And right now, at a tilt of 23.4 degrees, we're someplace right smack in between. And we think the last minimum, the last maximum was at 8700 BCE, before the Common Era, or you could say before Christ, and that the next minimum, when our tilt has been minimized, the next time our tilt will be minimized, will be at 11,000 in the year 11,800. So this isn't something that's happening overnight, but it is something that could affect our climate over long periods of time. And this is just one factor. And sometimes this changing of the tilt, a fancier word for tilt is sometimes given, is obliquity. Obliquity, but this is really just a fancy word for tilt. This changing of the obliquity, or changing of the tilt, is one of these changes in Earth's rotation or Earth's orbit around the sun that might have long-term cycles or effects on Earth's climate, and maybe they do help cause certain ice ages when they act together with each other over certain cycles. And broadly, this entire class of cycles are called Milankovitch cycles. Milankovitch. He was a Serbian scientist who was the guy who theorized that these changes in Earth's orbit might be responsible for long-term climate change, or maybe some cycles where we enter ice ages and get out of ice ages, or we have more extreme or less extreme weather. So these are Milankovitch cycles. And changes in the tilt, or the obliquity, are just one of the possible factors playing into Milankovitch cycles. And what I want to do in this video and the next view is talk about all of the different factors, or at least summarize all of the different factors. Now another one, this one is pretty intuitive for me, that this tilt can change. One that's a little bit less intuitive when you first think about it is something called precession. Precession. And the idea behind precession, I guess the best analogy I can think of, is if you imagine a top, or maybe you can imagine Earth as a top right over here. The top is spinning. The top is spinning in this direction. And obliquity tells you essentially how much it's wobbling. Well, actually, let me think of it this way. Imagine a wobbling top. So it's rotating like this. It's tilted. And then it is also, if you imagine that this was a pole up here that's coming out of the pole, if this was actually a physical arrow, that arrow itself would be rotating. So the best way to think about it is a wobbling top. If you think after some point of time this thing would wobble, so it would look like this. So now the arrow is pointing that way. And if you wait a few more seconds, now maybe the arrow is pointing a little bit out of the page. And then you wait a few more seconds, then it's pointing in this direction. Then it's pointing into the page. And so this whole time, the obliquity isn't changing. The obliquity, you can kind of view it as how far is that wobble. You could imagine how far from vertical is that wobble. And no matter where we are in that rotation, it hasn't changed. And you can imagine as the precession as where we are in the wobble. Where we are in the wobble. And this is a little bit hard to visualize, and hopefully as we think about it in different ways and I draw different diagrams, it'll make it a little bit clearer. But I want to make it clear, just as it takes a long time for the inclination to change from a minimum value to a maximum value and back, it takes a huge amount of time for Earth's precession to change in a significant way. So for this top to if you imagined this arrow popping out, for this arrow to actually trace out an entire loop, it takes 26,000 years. So 26,000 years to have an entire cycle of precession. Now what I want to do is think about, given that this precession is occurring, I want to think about how that would affect our seasons, or how it would actually affect how we think about the year, the calendar. So let's draw the orbit of Earth around the sun. So here is my sun right over here. and here is the orbit of Earth. And I'm not going to think too much. I'm going to assume that it's almost circular for the sake of this video. In future videos, we'll talk about how the eccentricity, or how elliptical the orbit is, can also affect the Milankovitch cycles, or play into the Milankovitch cycles. But let's just draw the orbit of Earth. Let me just draw the orbit of Earth around the sun over here. And so you can imagine this is at one point in time. This is the Earth. Let's say it is tilted towards the sun right now. So it is tilted towards the sun. And so if in the northern hemisphere, and I'm assuming this arrow is coming out of the North Pole, this would be the summer in the northern hemisphere. And then if you had no precession, absolutely no precession, when you go to this time of year, you still have the same direction of tilt. Let me do that in blue. You still have the same direction of tilt. We're still pointing to the same part of the universe. We still have the same North Star. You go to this time, we're still tilting in the same direction relative to the universe, but we're now tilting away from the sun. And now this would be the winter in the northern hemisphere. And we'd keep going around. If you had no precession, when you get back to this point over here, we'd be tilting in the exact same direction. If your obliquity, or if your tilt changed a little bit, you might move up or down, away or towards the sun a little bit. But this is all assuming no precession. Now I'm going to think about what happens if you do have precession. So what's happening with precession is when you go around one time around the sun, by the time you get to this point again, you're not pointing at exactly the same direction. You're now pointing a little bit further. So this arrow, let me draw it a little bit bigger. So this is the Earth, and this is that arrow. And this is hard to visualize, or at least it's hard for me to visualize. Well, once you get it, it's easier to visualize. But the first time I tried to understand it, it was hard for me to understand how precession was different than obliquity, or different than tilt. Obliquity is how much we're going from vertical. And so if we had no precession, we would be exactly pointing in that same direction every year. Now, with just precession alone, what happens is every year this arrow is slowly tracing out a circle that goes like this. So I'm going to exaggerate how much it's happening just so that you can visualize it. So maybe after several years, that arrow is not, when you're at that same point relative to the sun, that same point in the solar system, that arrow is no longer pointing in that direction. It has now traced out a little bit of that circle. So it is now pointing in this direction. It is now pointing in this direction. So if it is now pointing in this direction, will that same point in the solar system, that same point relative to the sun, that same exact point in the orbit, will it still be the summer in the northern hemisphere? Well, it won't, because we're now not pointing directly, or we're not most inclined to the sun at that point. Now we would have been most inclined to the sun a little bit earlier in the year, or a little bit earlier in the orbit. So we would have been most inclined to the sun. Maybe over here. Maybe over here. And it would take many actual thousands of years for it to get to be for the precession to change this much. But then over here, this is where, when at this point in that year, when we would be pointed most towards the sun. So what the real effect of precession is doing to our seasons, and doing to what our sense of what our year is that every year, relative to our orbit on Earth, because Earth is kind of a top that's slowly tracing out this circle with, I guess you could say, with its pole, what it's doing is it's making it tilt towards the sun, or away from the sun, a little bit earlier each year. A little bit earlier. I know it's hard to visualize, but you could even take a top out and have a basketball as the sun. And if you play with it, you'll see how that works. And precession is another one of those factors that play into, I should say, the Milankovitch cycles. And what we'll see is when you combine precession, or I should say change in precession, when you combine that with changes in tilt, and you combine that with changes in actual how circular or how elliptical the actual orbit is, and how that changes, then you might have a respectable way of explaining why Earth has entered into these climactic cycles over many tens of thousands of years.